There are no questions that go along with the 20-3 lecture. As you can see, there's really only 4 that are anything to do with the actual lecture itself, one of that being a title page, one of that being a slide that we saw from last time. So there's really not much new content today or anything else. The actual lecture is only going to be about 15 or 20 minutes. But because it's so short, I figured that we would also take the time here to dig into some review problems. Right, so some stuff kind of covering some of the old material that we have been looking at so far. It's a mixture of use. Part of it is because, the exam is not immediate, but it's coming up, right? So there's a couple of these things in here to kind of give you another recap on some of those old concepts that we've been looking at, a jump start to the review for those. And then on top of that, chapter 21 is kind of using a lot of what we talked about, especially in 18 and 19, but a little bit in 20. Chapter 21 is really kind of putting that stuff all together and how do we make heat engines out of this and a lot of that good stuff. So it's some good prep for that side as well. So let's go ahead and dig into it, right? So far in chapter 20 has been all about our microscopic view of the world, right? So 18 and 19 were all macroscopic, trying to piece together all of these different empirical laws that define gases and different substances. And then chapter 20, we said, okay, well, maybe they didn't at the time, but we know that matter is made up of a bunch of atoms. So how do we really marry these two descriptions together to say, okay, well, despite the fact that it acts like a really big ensemble, we know it's a bunch of individual pieces. What are the individual pieces doing to recreate those large-scale behaviors? And this is our final kind of thing on that. We've already seen the big points, right? We've already kind of got that description down, but I'd like to look at just 1 or 2 other things today to finish that out for us. So, first one being thermal interactions, right? We have seen this slide before. We have also discussed this picture before, right? This was one of the first pictures that we actually looked at when we were starting the course and thermodynamics in general. We said, okay, well, we don't know what temperature is, and we don't really know what heat is, and we don't have a great understanding of thermal energy, but I'm going to say that there's another way that we could possibly have energy. And we all just kind of took that at face value in the time and said, okay, well, let's set up, this structure of information that we have, a skeleton of a structure rather. And even though there's a lot of weird gaps, like we don't exactly have a definition for temperature, let's just focus on building that skeleton and then slotting things into it afterwards. And at this point, we've actually got pretty much everything filled in. Right? At this point, we do have some definitions for temperature. We understand that it's a measure of how fast the atoms are moving around, and we have equations that actually describe that. At this point, we also understand that heat is one of the ways that you can possibly transfer thermal energy between different systems or a system and its surrounding environment. We know that thermal energy is a measure of the energy contained inside the individual atoms, inside the individual, the structure inside of our substance, and that depends on temperature and is a state variable. And then we could also say, okay, well, we know about temperature and how that relates to the energy in individual particles, right? That was really kind of a groundbreaking part where we had kinetic theory to give us what we have for pressure and temperature. So we're here. We've got it. We've finished most of our description of what's going on here. We still have a few different things, and chapter 21 is going to dig into engines specifically, so making use of all of this stuff that we've seen so far. And we've got 1 or 2 new laws to look at in that chapter, but for the most part, we've really got most of our definitions down at this point. So let's test this with a concept question. I have 2 boxes. They haven't been mixed yet, but they're 2 boxes side by side, insulating, no heat going in or out or anything else like that. Box A has 1,000 particles and a total thermal energy of 2 times 10 to the negative 17th joules. Box B has 2,000 particles and a thermal energy of 3 times 10 to the negative 17th joules. So, of these 2 boxes, which one, if either, has the higher temperature? So let's think about it like this. Thermal energy can be expressed as the sum of the individual energies of every single particle, right? And that's a really, we're basically taking every single particle, measure its kinetic energy, put it into a bin, right? And then we add all of the particles up, and that should be our total thermal energy. Statistically, it's equivalent to instead say, well, what if we just took, instead of calculating the actual value for every single particle, what if we just took the average and multiplied it by the total number of particles? That should give us the exact same answer. And it does, right? That's statistics. But now I look at this and I say, okay, well, E thermal is equal to the number of particles times the average kinetic energy per particle. And if we even go back to this last slide, we kind of remember that temperature changes as long as there is a difference between the average kinetic energy between particles. What that's really saying is that average energy of particles goes along with temperature, right? T1 is equal to T2 if and only if, which is how you write that phrase out, average energy of 1 is equal to average energy of 2. So really, we can rewrite these answers as average energy A is greater than B, energy of A is equal to B, or energy of A is less than B. And now you see where I might be going with this, because we can just rewrite this to say that that average kinetic energy is equal to the total thermal energy divided by the number of particles. And if we do it like that, A should be our answer. The average energy per particle in box A is greater than in B. So, one thing that we haven't really talked about too much, and in great detail we really won't, is entropy. It's a really neat thing. It's very important, right? I'm not going to try and pretend like it's not something that's not important. If you're in chemistry, this will be significantly more important for you. But we really don't do too much with this until you get into higher level courses. So I know I've brought it up before, but it's roughly speaking a measure of the disorder in a system. And that's, I think, a little bit unclear what exactly it means. And we've used that example of a wine glass with some wine in it, and then you smash it on the ground because you're terrible at parties. And clearly the shattered and spilled all over the place is more disorderly, mostly because think about how easy it is to go from a full glass in one piece to a billion pieces shattered on the ground, right? That transition was very easy to do, but to suddenly be able to reform that back, all of the wine is back in the cup and the glass is back in one piece, that's very difficult to do. So that's a process by which entropy would increase. But I don't think this really translates super well when you're talking about like particles in boxes or something like that. So just like all of our other things, there are two different descriptions that we might take for entropy. And one of these is looking at essentially the difference between entropy and states. How much heat might it take to change relative to a certain temperature? But this one is actually substantially more confusing, I think. I don't think this one's nearly as easy to visualize. If you use it, it can be very powerful and very useful. And I mean, you do need it when you start working in thermodynamics. But exactly how this can be used to calculate entropy, I think, is a little bit less clear than the microscopic description. Because the microscopic description is actually just, well, statistics. Right? I think this picture down here, it kind of gets to the point, but maybe not completely. Ordered is when I have a bunch of high energy particles separated on one side and a bunch of low energy particles separated on the other. Disordered is when those high energy particles are separated everywhere. But let me describe this in a little bit of a different way. Let's imagine we have two bins. Bin A, bin B. And let's say I have 50 particles that I want to put in each bin, right? I want to split up and I want to assign these particles to the two bins. I take bin 1, or particle 1. My words are getting all mixed up today. I take particle 1. I say, okay, there's a 50-50 chance it's going to go in bin A, bin B. Blindfold, toss it, see where it lands. I do that for all 50 particles. What's the likelihood that I end up with all 50 particles in bin A? I'm not actually going to ask you to calculate that one. It's tiny. It's very incredibly unlikely. But it does have a possibility, and it is something that's there, right? Now, consider instead the scenario where instead of all 50 being in bin A, I have 49 in bin A and 1 in bin B. That's a lot more likely, right? And there's a lot more different ways that we could possibly get there, which is really the important part, right? Because my very first particle could end up in bin B, and then I've got 49 in bin A. Or perhaps my first one goes to bin A, but then the second one goes in bin B, and from there on, all into bin A, right? We can see that there's 50 different possible ways that we could end up in that scenario. There's 50 different circumstances where I could end up with my single particle in bin B, and then everything else would have to be bin A. Whereas for A, there's really only one way that can happen, right? There's one direct path, all of them go into A. If any of them go into B, that's not our path anymore. So the entropy of system A would be a very low value because it would be KB log of 1, right? W is literally the number of different orientations that could give us our result, the number of different pathways that could get us to that result. Whereas bin B has a much higher entropy because there are 50 different ways. And now imagine we take it one step further and we say, okay, 47 bins in bin A, 3 particles in bin B. Now we're growing the number of possibilities, the number of possible paths to get to that particular end result. And that's really another way that we can describe what entropy is. The higher entropy is more possibilities to get to that one particular place. It's the more likely scenario. So it's kind of like this. You have to imagine that this is an unlikely scenario, right? Having T1 be greater than T2, if these are connected systems, it's unlikely. You would have to have a bunch of high energy particles separated to the left side and a bunch of low energy particles separated to the right side. And it's possible. Of course it is. There's all sorts of random motion going on between all of these different particles, and it's a possible scenario that you take a snapshot and you find a bunch of high energy particles on the left side and a bunch of low energy on the right. But the likelihood of taking that picture is significantly lower than seeing both sides be just about the exact same. And that's kind of our description that the universe trends towards higher entropy, right? It's kind of like one of those phrases that the house always wins, entropy always increases. You might see small local cases where it goes the opposite direction, where we become spontaneously more ordered than we were. But if you take it over a long enough time, you average it out, entropy is always going to end up increasing. Does that make sense? We're mostly dealing with entropy in a conceptual sense in this course. For our first problem, as we've got it, I've got 3 different gases, and I'd like you to plot out each of the series of transformations that they go through, right? But when I'm talking about plotting these things out, I mean not just a kind of a broad description. I would like to see, accurate tick marks for where these things are ending up. So drawing and labeling properly the graphs for these, and that means you actually have to know how the transformations change those individual state variables. But anyways, I'd like us to just start with gas 1. Try to do these in order because that's the order that I'm going to go through these. But I'm going to go over gas 1 first and then give you some more time to work on the others afterwards because, I'd like to show you my process And that way, hopefully, if you got a little bit stuck on the first one, you can make some progress on 2 and 3. Okay, I'd just like to start to take a look at just what's going on with gas 1. And this is going to be kind of an ugly picture. I had a little bit of forewarning here. So what we've got in order, and let's go ahead and draw out some good stuff first. So we'll say gas 1. Let's go ahead and set up what our chart should actually look like. And while I'm here, I'm going to put in some tick marks too. And I've got an idea of where things are going to go, right? So if you're doing this for the first time, it might be helpful to just have a really rough drawing to begin with and then say, okay, well, I have a general sense of how these things are going to move around at first. And that helps me visualize it. But now once I calculate some more exact values, I can actually get this thing accurate. So I know, because I've solved this, we're going to need these points. So I'm going to call this point P1. Put those tick marks in, and I'm going to call this point V1. So this is 2 times V1, and this is 3 times P1, right? We're putting everything into terms of P1 and V1, all these initial states. And this is not something that we've done a ton of yet, but it's going to be something that's very useful, and we're going to keep using it, especially as we go into the next chapter. So, just a little bit. I think that's gotten bumped down a tiny bit there. So we start at step 1. And the first one's nice and easy. Because the first one, they say, okay, and we'll color code all of these. Step 1, constant pressure, double the volume. Constant pressure, double the volume. We end up right here, right? And we'll mark that, and we'll send that all the way over there. And then we'll make sure that it actually meets that second point, give it a little bit extra. Going that way, label this point 2. Okay? So that one's not too bad. Right now, we're looking at the next step. And this is going to be an isothermal transition to pressure is quadrupled. So let's say P3 is equal to 4 times P1. So I'd like to write that out. So 4 times P1, okay, so we need somewhere up here, but where exactly? Is it over here, over here? We don't exactly know. So here's where I mean that we need to start solving these things out. I'm going to start by, we know it's an isothermal transition. So P2 V2 is equal to P3 V3. Then what I can do is I can start plugging in common variables, right? I said I wanted to put all of this stuff in terms of P1. So I'll say, okay, well, P2 is still equal to P1. V2 is 2 times V1. I already know that P3 is 4 times P1. And I'm just trying to figure out where I should put V3. So let's rearrange this a little bit, cross out those, divide over by the 4, and what we find is that V3 is equal to 1/2 of V1. So we can go up here, 1/2 times 4P1. Let's rotate this thing a little bit so that I can actually draw it. Because remember, Mastery knows, you know, and I know that this should be not a diagonal line, it should be a curve. And maybe it looks terrible, but you know what? That's okay. We're not super worried about it. So that's point 3. Now, the last one, the weirdest one, is going to be an adiabatic expansion. Adiabatic to V4 is equal to V1. So, since it's an adiabatic expansion, I know P3V3 to the gamma power is equal to P4V4 to the gamma power. And what I can say also is that since I am dealing with a diatomic gas, this right here should be, did I say diatomic or monatomic? Monatomic. Sorry. Erase that. Not 7/5, 5/3. With those values, we do our exact same steps as last time. We say, okay, we are starting at 4p1. We are starting at 1/2 v1 is equal to mystery value p4 times, we go back to our initial value v1. And with all of those, I'm going to do a little bit of rearranging. Again, I'm looking for p4 here. But what I can do is I can divide both sides by v1 to the gamma power, right? And I can essentially just eliminate that thing out. This is going to turn into 4 times p1 times 1/2 to the gamma power, right? We plug all of this stuff in, we should find a final value of about 1.26 times p1. So, go back up to our graph. We can safely put in our 4th point. So we're about halfway between these two tick marks. Is that right? No, that's not right. This is 3p1, this is 2p1, so about 1/4 of the way up, actually. It's really close, but it's not quite exact. We didn't quite reach back to our initial point. We got kind of close. So again, a little bit of rotation so this doesn't look terrible. Something like that. And that'll be state 4. Okay, so let's go ahead and take a look at it. Let's go through these other two and see what we've got. Let me pull up all of these different chats and everything else. So gas 2 is actually the easiest one here. Diatomic gas, isochorically brought to 1/3 of its initial pressure, isobarically expanded, and then finally isothermally compressed. There's no adiabatic process here. So as long as there's no adiabatic process, it doesn't actually matter that it's a diatomic gas because that only shows up when we're dealing with an adiabatic transformation. We're in luck then. So I'm going to kind of take this just in order though, and this one's not going to be super long. I don't even really need any equations for this one, to be honest. There's nothing really crazy to calculate. So let's start by saying, okay, gas 2. One piece of that set up, 2 pieces of that set up. And I've got a little bit of insight as to where some of these values are going to be going. Once again, you might draw out a beginning sketch before you dive all the way into it, or figure out what some of these values are before you go all the way into it. So there's 2, there's 3, so this is 3v1. This is 1/3 of p1. And we start right here. First step. Isochorically compress, or isochorically down to 1/3 of its volume. That's what I should be saying. It's not a compression. There's no change in volume. I really should be saying decrease in temperature if I'm going to say anything. So there's step 1. Then we expand to 3 times our original volume while holding the same pressure. So we're going to go all the way across like that. And then finally, an isothermal. So I'm going to have to draw a slight curve to this one. Oh, and let's pretend that that's a good looking curve. And that's what we've got. So it actually turns out to be not so bad. Right? There's nothing really crazy to solve for in this one, especially because the isothermal goes right back to where we started in the first place. But really, I just want to give you guys some experience with looking at these multi-step parts, because as we get into chapter 21, they really start to dominate. So I wanted to make sure that we've got some practice with these things before we get all the way into that one. Okay. Gas 3 is a weird one. Gas 3's got some work involved. We're going to go essentially in both directions for this one. So I'm going to put my initial tick marks kind of right in the middle here. So I'm going to have, let's say, half. There's 1. There's 3 halves. There's 2. So this up here at the top is 2p1. This right here is just p1. And we're going to have 1, 2, 3, 4. Same kind of deal. v1, 2 times v1. So we're going to start right here in the middle. Now, we got some weird things going on with this one, right? The very first one, what we've got is an isothermal expansion. So back to my color coding technique here. Step 1, isothermal to V2 is equal to 2 times V1. Right there. Okay? Well, what we can do then is we can say, all right, as long as we are an isothermal transformation, then I know this equation right here applies. P1V1 is equal to P2V2. I want to put everything in terms of my initial variables. So I'm going to plug in for P2. That's the step that we go down. We can say, okay, V1, V1, we don't need those anymore. And you might have done this without any sort of equation for this one, but P2 should be 1/2 P1. That's really what we got for step 1. So 2 times the volume, 1/2 the pressure, something like that. Here is state 1, here is state 2, and again, need a little bit of a curve between these 2 points. Something like that. Perfect. Okay. Step 2. Time to get messy. All right, because now we have an adiabatic compression. So let's start with this. Let's just start by talking about adiabatic. So V3 is back equal to V1, right? And we know it's more steep than the isotherm because it's an adiabat, but it's going to be somewhere up here, but it's not yet clear where. So we're really actually going to have to solve out for that one. It might help to remember, since we are a monatomic gas, gamma is still 5/3 as it was in gas 1, and that matters here. So what I'm going to do is essentially the exact same steps here, but now it's with the adiabat equation. So P2 V2 to the gamma power is equal to P3 V3 to the gamma power. Start plugging in some of these things that we actually know. We'll say, all right, well, we know that P2 is actually 1/2 of P1. We know that V2 is actually 2 times V1. We know that P3 is something, and we know that V3 is V1 to the gamma. I'll divide over by V1 to the gamma, and that means that this is going to turn into 1/2 P1 times, well, 2 to the gamma power. And you could solve this out right now, and that would be fantastic. I would like to keep this as an exact number because it helps me a little bit at least. So what I'll do is I'll say, all right, well, this is 2 to the gamma power. 2 to the gamma power divided by 2. Anything to the anything power is now to the power minus 1, right? So I can redefine this and say, okay, well, this is really P1 times 2 to the gamma minus 1 power. But now we do need to have some decimal for this because I need to know where to put it on the graph. So this will be 1.587 times P1. This just helps it stay nice and exact, right? It's an easy way to write down an exact number. So that'll go back. We put it at 1.5, so it's a little bit above that second tick mark. About right there. Again, give it a little bit of rotation so I can draw this properly. And we'll go something like that. Okay? Now, we are going to go the other direction, right? We're going to compress this thing isothermally. So what we know is we're going to go all the way up to 2 times P1. So isothermal, so P4 is equal to 2P1. Okay, same thing as before. P3V3 is equal to P4V4. Plug in with the values that we've got. Ugh, it gets a little bit nasty now, right? As we start to chain these things together, sometimes they can get a little bit disgusting, but that's okay. So this is going to turn into 2 to the gamma minus 1 times P1. V3 was just V1 again. P4 is now supposed to be 2 times P1. And we're trying to figure out where does this thing fall on the x-axis. So we have that. And I'm going to take my same trick as last time, actually. First, I'm going to cancel out the P1s. And then I'm going to say, okay, well, I'm just dividing by another 2. So this is going to turn into V1 times 2 to the gamma minus 2 now is equal to V4. Which, if I plug that number in, this should be something like 0.794 times V1. So this is about... Did I do this a little bit weird in the last one? That's okay. So this will be like a little bit more than halfway over, but we're going to be somewhere around right here. Oh, I didn't draw. Yeah, there we go. That's fine. Sorry. Confusing myself a little bit. I was thinking a step ahead. So we get something just like that. Goes up by a little bit, and it should be a little bit more gradual than the other one. And then finally, the last one is just an adiabat down to our initial states. So it'll be kind of sharply vertical again, like that. Kind of a nasty shape, but it gets there. Gets the job done. Go ahead and write that in. Step 4, adiabat to initial. That, and the last one, unlike our first one, are what we would call a closed loop. So this is something that we might use for a heat engine. And actually, this process in particular, this swapping back and forth between adiabats and isotherms, that's actually a pretty important thing. I don't think that we end up discussing it much in this course, but it's actually how you try to make a perfect engine. So, kind of a neat thing. Got a little bit of extra history to it. Anyways, I'm going to do these things out of order because I don't think we have time for all of them, and I'm having some real issues with problem 2. Fundamentally having some issues with problem 2. So, let's go ahead and skip these. I'm going to do these kind of in order of importance right now. So let's start with this one right here. It shouldn't take a ton of time, actually. I'll leave you to it. Okay, so let's start to take a look at this one. And right off the bat, as we start to take a look at it, right, one of these is much easier than the other. And why might that be? See, both of these are special processes, which means certain things are 0, or certain things are unchanging. And for adiabats in particular, remember that an adiabatic process is a process in which, so let's write this out. An adiabatic process is a process in which the heat exchanged is equal to 0. There's no heat exchanged. Right? The entire idea of the adiabatic process is that it goes really, really fast so that there's no time for heat to be exchanged. So then, that solves that one. Now, the isothermal, that's a little bit different, but it still has a value that's going to be 0 for us, right? And instead of being heat, it's thermal energy. So the change of thermal energy is supposed to be equal to 0. And we know that thermal energy is made up of a heat exchange and work exchange. And we can see that there is clearly some area under the curve. There is clearly some work being done. Then what we can also say is, all right, well, with all that stuff, then Q should be equal to negative W. Right? For an isothermal, we already have this worked out for us. So this is a negative of a negative, so it's going to turn into positive nRT, natural log of VF over VI. Fantastic. The only problem we run into is we need to actually know what T is first, right? It's the same temperature, but we don't know what it is. So we're going to go ahead and use the ideal gas law real quick. And I'm just going to take my initial states to plug in some things, but you can take either state if you'd like. When I plug all of this stuff in, I should find a value something like 365.6 Kelvin. Take that value, and I'm going to go back up here, and I'm going to say, okay, well, I really don't want to convert the volumes again if I don't need to. So what I can do instead is, so nRT natural log of VF over VI, that's 1,000 over 3,000. Or 1 over 3. We don't have to worry about any units. It works itself out. Plug in the other values that we've got for the number of moles and for the temperature we just found, and the heat, in this case, exchange should be something like negative 334 joules. So here's the premise. You are making brass in some sort of factory. You've got 4 kilograms of liquid copper, 3.5 kilograms of liquid zinc. Each of those, I just got them to the temperature they need to be melting, right? So they are completely liquid. They have melted at this point, but I haven't added a bunch of heat to make them hotter than that. Some emergency pops up. You slam the emergency cool button, right? And both of these buckets pour into a vat of water below to rapidly cool these 2 samples down. After everything has kind of steamed off, you look at like maybe there's marking lines in the vat or something like that. You realize that 20% of that water has boiled away. By the time everything is coming to equilibrium, 20% of the water has boiled away into steam and has gone off. How many kilograms of water would have initially been in the vat? So again, the setup is really the most important part, right? If you can get the setup, that's really the main thing that I'm looking for in this one. But we have all of these different values to deal with, right? We've got the temperature that each of these things is going to be melting or boiling in the case of water. We've got the heats of fusion, and we've also got the specific heats in the phases that they're in currently. So we've got to kind of keep all of that in mind. Leaving this in Celsius is totally fine. Remember, we're dealing with just a bunch of delta T's, so that's not a worry. But one of the most important things we need to deal with here is we know that this melting temperature, the melting temperature for each is really the temperature that it starts at for each of these materials. But then we've also got our water starting at 30 degrees. What temperature does everything end at? Temperature has to be 100 degrees Celsius, because it's partway through boiling, right? 20% of this has boiled off into steam, and if we remember right, there's no temperature change that can happen during a phase change. So if everything's mixed together, everything's at the exact same temperature this entire time, we're partway through that boiling temperature, right? We're partway through that boiling process. We're at the boiling temperature, 100 degrees Celsius. So TF should be 100 degrees Celsius. And once we've got that, we've really got all of the pieces we need for this thing. We just need to set it up into one really big equation. So I'm going to call each of these things, I'm just going to go with some subscripts here. As I would set this up, we're going to say, okay, it's all mixed together in one system. So Q net is equal to 0. And then I'm going to consider, okay, here is the copper. So mass of copper times the heat for copper. That's going from liquid to solid. Do the same thing for zinc. And I know I'm like mixing up all the subscripts and everything else. I want to try and keep it straight because we've got a lot of M's, we got a lot of L's, we got a lot of C's. So this hopefully just makes it a little bit easier to read. So those were negative because it's liquid to solid. That loses heat. And then the temperature changes, remember, these are always just positive. Or rather, we just add them because delta T takes care of that minus sign for us. So MC, CC, and then we're just going to call this delta TC, right? The difference between melting temperature and 100 degrees Celsius. Same thing for zinc. Now, the water's where it's going to get a little bit more weird. So first I'm going to do the temperature change for the water, which is totally identical for this one so far. But now for this last term, not all of the water has boiled. And that's really the trick. It is only 20% of the water that ended up boiling off. So that point 2 is the really important bit. It's the only tricky part of this, the big setup, honestly. But once you've got that, if I look through this whole thing, we've got a lot of variables that are given to us. So as it turns out, the only thing that we don't actually have is the mass of water. At this point, we've got everything else. So what I can do, I'll combine all this stuff together, and I should end up with, let's see here. Oh, shoot. Do I still have this number in my calculator? I don't. Oh, shoot. I don't remember what it is. This term right here should turn into something like mass of water times 745,300. I'm going to go back to my old slide on this one. 242, 8100. For that one. Right? For a final value, the mass of the water should be something like 3.26 kilograms. Okay. But as far as the problem goes, the idea is that you have a U-shaped tube. It's closed at one end, it's open at the other. You very, very, very carefully funnel in some mercury on top of this thing so that none of that air that's already in the tube can escape. At a certain point, it kind of balances out, right? You're not able to pour any more mercury in. It stays at a level spot. It doesn't sink down or anything like that. How tall is that tube of mercury going to be then? What is this length L as seen in the picture? What they really should have specified, and what I'm very unhappy that they didn't, is that this value right here, this 20 degrees Celsius, is a constant for this problem. It's the only way to solve this problem is if you have a constant temperature. So let's start by getting this thing in a good spot for us to actually work on. Move this down here a little bit so we can remember which problem that we're looking at. Okay. So if we are sitting at a constant temperature, then the air has this equation that describes what goes on between it, right? From when it was just in the open tube to where it is now. We're given that pressure 1 is just 1 atmosphere. V1 is difficult. We know that the tube is a length of 1 meter, but we don't really have any idea, like, what's the diameter of the tube. So what I'm going to do for now is I'm going to say that this is 1 meter times an area A, and that's whatever the area, the cross-sectional area of this tube is. And we just kind of got to go with it for now. But that's okay, right? We also have that the density of mercury is 13,600 kilograms per cubic meter. And that's another important bit. So this is a fluid with some height difference, right? What's really important here is that right at this point, there's a hydrostatic pressure that is greater than 1 atmosphere. Right? So what we can do is we can say, okay, well, we remember that, like, when we were dealing with pistons or anything else like that, that if I can calculate the pressure at any one point in the gas, if I have a piston or a certain spot within my container that I can measure the pressure on that particular spot, it's the same pressure throughout the entire gas. So if we can find the pressure at this particular spot, we have the pressure for the entire gas. So what we can do then is we can say, okay, well, P2, I remember my hydrostatic pressure equation. The pressure at the very top, atmospheric pressure, plus rho times G times L. And with that, we have an expression. Even if we don't have an exact value, we have an expression for what P2 should be. Right? We know the length of the tube. We're looking for L. So I'll put that in here. Find L. Okay, well, that works really well for that one, but we're going to still run into a little bit of an issue, because even if I plug in this stuff as is, this is not enough information to find L. I still don't know V2. So let me go through the same process for V2 here. Let me say, okay, well, V2 is now not the full tube. I was 1 times A, but now I have lost some of that length of the tube. Or better yet, let's just pull A to the outside. And this might seem like we're going backwards, because now we have another variable that we don't know. But that was actually going to show up in V1 anyways. So now what we can do is we can take all these things and plug them all into one equation together. So P1, that's just a value that we've got. And I'm going to plug in, so this is 1 times A for V1 times P1 plus rho GL times A times 1 minus L. Okay, and I said we are in luck because we can cancel out the A from each side, so that's no worry. And now I'm going to distribute what's here on the right side. So I'm going to get P1 times 1, rho GL times 1. And then we have minus L times P1 minus rho GL squared. Still equal to P1 on the other side. Cancel out those two. 0 is equal to, I see a bunch of terms with L, right? So I'm just going to divide the entire thing by L, actually. Rho G minus P1 minus rho G L. Move some things over, divide some other things. And that's our final expression. When we plug everything in, we should find something 24 centimeters. So it's a neat little problem, I think. I like it. I'm a big fan of these ones. I know we don't do a ton of stuff with hydrostatic pressure, though, so this was part of the reason why I picked it. I don't know. I was just trying to pin down why we were using certain things in the solution, though. And it became apparent that they just decided not to tell us the temperature was supposed to be constant. Like, realistically, it shouldn't be. Like, there is a slight temperature difference when you compress it like that. It's not a huge change, but there is a little bit of one. Maybe they were trying to imply it by saying that it's not an insulated tube, but I think that's kind of a shitty assumption to make. How it goes sometimes. But anyways, I think that'll close out for everything that we're doing today.